All right, so now that we know how to classify a solution as either acidic or basic, we want to look at solutions of strong acids, strong bases, or weak acids and weak bases. Here's a general equation for an acid. Going forward, the acid should be the hydrogen donor. So this is HA, whatever this is, it's the acid. If I look at its partner on the other side, I can tell, oh yeah, HA donated its hydrogen. If this guy wants to go in reverse, A needs to gain a hydrogen. The hydrogen acceptor is acting like a base, and on the product side we call it the conjugate base. So if A wants to go back to the original acid, he needs to be a hydrogen acceptor. He's the conjugate base of the original acid. They go in pairs. And again, conjugate acid-base pairs only differ by a hydrogen. Same kind of deal in the middle. In the middle here we have water. If H2O goes forward, I can tell, oh yeah, H2O was the hydrogen acceptor. Going forward, water's acting like a base. If this H3O particle wants to go back to the original, then he becomes the hydrogen donor. We call him the conjugate acid. Acid-base pairs differ by just a hydrogen. Excellent. Okay, so now how do we classify this as either a strong acid or a weak acid? It's all about the K value. You can't escape these equilibrium constants. You're going to love them. We call this an acid dissociation constant, and they'll label it as Ka. It looks just like any other K value. We set it up as products over reactants. We raise them to the ratio in the balanced equation, which this is all 1-to-1s. And notice that we do not have water listed in the Ka expression, the equilibrium expression. There is no water. Because he's a liquid. And we have no pure liquids. Or solids, which we don't obviously have any solids. But when we set up equilibrium expressions, we do not include pure liquids or solids. So you will not include the water. Now there are a few different ways that you can see these acidic reactions written. You could see it written kind of like this. So I could write hydrochloric acid. I could write this as HCl. Let's say that A is chlorine. So I could write HCl plus water. And then I could have like a double-sided arrow. I could do that. And then I could write this as H3O plus chlorine. H3O is called the hydronium ion. It's basically just a hydrogen attached to a water molecule, which, these are all solutions. So if HCl donates a hydrogen, you've got this little positive hydrogen swimming around in the water, and last I checked, the oxygen end of a water molecule is negative. So often those little hydrogen ions are attracted to the water molecules, and they end up kind of looking like that. H3O. We call this guy hydronium. The hydronium ion. Now sometimes you might also see, especially a strong acid like HCl, you might see this written like this, just forming hydrogen and chlorine. You might see it written like that, and it's totally fine. We're not going to include the water in the equilibrium expression anyways, so they kind of show you two examples. One has water, one doesn't. And they also kind of show that you could either put the hydrogen as hydronium, where, the hydrogen ion will be attracted to water molecules, so often it looks like H3O+. Or you could leave it as just like free-floating hydrogen ions, H+. Either is the sign of an acidic solution. In reality, a lot of those hydrogen ions are attracted to the water molecules, but if you write it in your equation as just H+, that's okay. Now here's the other thing that happens with these acids, in particular strong acids. Think about HCl. we've always kind of said that this thing dissociates 100%. So often you only see this as a one-sided arrow. I mean, if HCl dissociates 100%, those ions usually stay in solution. They're very stable ions in solution. You know, if I started with 1 mole of HCl, I get 1 mole of hydrogen and 1 mole of chlorine. 100% dissociation. Well, look what that's going to do to your Ka value then. You're going to have almost all products. Ka is still products over reactants. This thing is like almost 100% hydrogen and chlorine ions. The amount of neutral HCl molecules is ridiculously small. So we say the equilibrium lies far to the right, or we might say that it lies far forward. So sometimes with strong acids like HCl, you might not see the double-sided arrow, which is fine. Either way is fine. If I see the double-sided arrow, I might be given a K value. For example, the K value of HCl is giant. For HCl, Ka, it's like approximately 1 times 10 to the 8. It's huge. So if they kind of set this up as an equilibrium expression with a double-sided arrow, look at your giant K value. Well, that should kind of help me to look at this and say, well, yeah, there's a chance that it could go reverse, but this thing really favors the forward, big time. Super large K values for strong acids, which makes sense. Products over reactants, we really have almost all products. This thing is like almost 100% dissociated at equilibrium. Which means then that a strong acid produces a weak conjugate base. So we said the conjugate base, in this case, would be like the chlorine conjugate base. Since this thing really doesn't go backwards, it means that chlorine really does not have a high attraction for that hydrogen ion. They really stay dissociated. Right here it says a low affinity for a proton, which really is a hydrogen ion. Yeah, I mean, if that chlorine ion was really acting like a base, he would pick up the hydrogen and send this thing in reverse, and we go back to the neutral HCl molecule. That really doesn't happen with a strong acid. It stays dissociated. So the conjugate base of a strong acid is usually a really weak base. Think about this too. Almost everything with chlorine is highly soluble, aqueous. So I mean, really, chlorine doesn't have any business picking up hydrogen and making a neutral compound, because HCl is so soluble, it's so aqueous. So we say that chlorine is a really weak conjugate base. Common acids, strong acids. I think we kind of mentioned these earlier in about chapter 4. Strong acids are usually things that you're really familiar with, like the hydrochloric acid, the nitric acid, the sulfuric acid. Those are the ones that we use most often in the lab. So they're the most common examples listed. Other strong acids are hydrobromic and hydroiodic, as well as perchloric, which I usually kind of remember then that the halogens make strong acids, except for fluorine, which we'll talk about. Hydrofluoric is a weak acid. And then I usually kind of remember that perchloric, because hydrochloric is like the first thing that jumps into my mind as a strong acid. So this perchloric is also a strong acid. We should be familiar with some common strong acids. Okay, so what about weak acids? Well, this makes sense then. A weak acid has a really small K value. Weak acids really don't favor the forward by much. So a good example, like one of the most common examples of a weak acid is acetic. Most common example. It could be written one of two ways. Sometimes you might see this, the CH3COOH. This is kind of the organic way of writing it, where, it's trying to show you the structure. You'll have a carbon surrounded by 3 hydrogen. Then there's another carbon with a double bonded oxygen and an OH group. So that's kind of the OOH at the end. This is totally acceptable, it's totally fine. Often you'll see this written as an equilibrium expression with water. And often you don't have to write these equations, they're written for you. Okay, so this guy here is an acid. It's a weak acid, but nonetheless, it's an acid. It's a hydrogen donor. Okay, so on the product side, what you're left with is this, CH3COO. It's this last little hydrogen that's, whoop, gone. This thing then has a charge of -1. Okay, so where did the hydrogen go? This poor little hydrogen gets donated to the water. So the other product is H3O plus 1. That hydronium ion. Oh, cool. Okay, so we're going to call water then a base. Water was the hydrogen acceptor. And again, since this is an equilibrium expression, if I want to send it backwards, the pair to the acid is a conjugate base. This guy's the conjugate base. It's the acetate ion. If I want to send this guy back to the original, then he's got to gain a hydrogen. He's got to be a hydrogen acceptor. H3O is the conjugate acid. If I want to send this hydronium ion back to the original water, then he's got to donate his extra hydrogen. Now, I should just make note. You might also see this written in more of like an ionic way. Sometimes they'll write this as hydrogen acetate, 2H3O2, which again, then it's going to lose this first hydrogen. And sometimes they might write the product as the acetate ion, C2H3O2 minus 1. Either is totally acceptable. Very, very common example of a weak acid. Okay, so now with a weak acid, we usually said that, maybe this happens by like 1%. Maybe this thing is like 1% dissociation. Dissociation. Weak acid, most of the particles are still the neutral acetic acid molecule. It might go forward, and yes, the product is acidic. We'll have that H3O plus ion, the hydronium ion form. It's always a sign of an acidic solution, but not by much. If I had 100 molecules, maybe 1 out of 100 will actually go forward and make ions. So if you think about Ka as products over reactants, and now I'm really not making a lot of product, then it kind of makes sense that Ka is small. The equilibrium lies far to the left, or we might say reverse. It favors the original reactant. There are not a lot of ions in the solution. Cool. So it says then the conjugate base of a weak acid is relatively strong. Like this guy here, this acetate ion, he's a stronger base than the water. This guy here has a better chance of picking up the hydrogen and sending it in reverse than water does going forward. Going forward, water is obviously not a strong base. Can water accept hydrogen? Well, yeah, but it's not like his first choice. But that acetate ion would love to go back to the neutral particle. That acetate ion has a better chance of picking up the hydrogen and sending this thing in reverse. Common weak acids. A lot of organic acids are weak. So like formic acid, acetic acid, citric acid. Other ones that I might make note of, hydrofluoric is a weak acid. Hydrochloric, bromic, iodic, the rest of the halogens do form strong acids, but not hydrofluoric. There's a very strong attraction between that hydrogen and fluorine. It's like as close to ionic as you can get without the electron being completely transferred. It's a very strong attraction. Other ones too that are kind of common, phosphoric and carbonic acids are weak. Now again, what if I'm like given something and I'm not really sure if it's strong acid, weak acid? If it's not something that's real common, look at its K value. If its K value is small, and by small we mean like 10 to the negative something, that's probably a weak acid. It's not going to go forward and produce many ions. Strong acids have gigantic K values. Okay, so here's what we can do with this. Here's a good example of a hydrofluoric acid solution. Now again, sometimes they'll write it like this. Sometimes, just to make note, they might also write it like this. They might go HF plus water. And then on the product side, instead of this being like free-floating hydrogen, they might have it as H3O, the hydronium ion, and then we'd have the fluorine. Often you'll see it written with water for a weak acid. Often strong acids leave the water out. But again, you usually don't need to worry about writing the equations. They're often given for you. Let's see, what do we have here? A weak acid, which again, might only go forward by like 1% maybe. So I'm starting with a 1 molar solution of HF. Okay, so 1 molar solution of HF. But since it's a weak acid, it's not going forward by much. So I might have 1 mole per liter of that original HF, but I'm not dissociating 100%. So whatever I get on the product side, these ion concentrations are going to be very small. Super small, let's just say that. Not the same as if this were a strong acid. What if this was like HCl? And this dissociates by 100% to form hydrogen ions and chlorine ions. Now if this thing starts out 1 molar and it completely dissociates, we should get 1 mole of hydrogen per liter and 1 mole of chlorine per liter. That will not be the case with HCl. And we can get rid of that guy too. This thing might shift forward, but not by much. Oopsie, I crossed off the wrong one. We want that one. Will we produce hydrogen? Yes. But it'll be less than 1 mole per liter. We're not dissociating by 100%. However, we can say this. I crossed off the wrong one before. The hydrogen and the fluorine will be formed at a 1-to-1 ratio. So whatever I get for hydrogen, it should be the same as the amount of fluorine formed. But it's just not going to be 1 mole per liter like I would have in something like HCl, a strong acid. Now this guy, it tells me it's a weak acid. So will the fluorine concentration be greater than 1 molar? Absolutely not. That's crazy. If we're starting with 1 molar, how can we produce more than 1 mole of fluorine? Same thing with the hydrogen. It would be impossible to produce more than 1 mole of hydrogen. So really, that's all we can say. Yes, we'll produce hydrogen, not a lot. It'll be less than 1 molar. But I can say that the hydrogen and fluorine ions will be formed in a 1-to-1 ratio.